Okay, welcome to CSC148 Lab 5. This week there are no labs because you guys have a test today. So there's this recording, and Lab 5 is going to be based on this week's content of linked lists. So the learning outcomes, you will be able to implement linked list methods using iteration, run some timing experiments to compare multiple implementations of an interface, and then augment the implementation of a class by adding new attributes. So there's two starter files, linklist.py and timelist.py, and I've already downloaded them. And let's see, here's some advice. Draw lots of pictures. Pictures will help you understand what your linked list structures should look like before, during, and after operations that change or mutate those structures. If you skip the drawing, you are much more likely to make mistakes. We'll see about that one. Be sure that you know exactly what attribute each part of your drawing represents. This will guide your code. Your linklist.py file will become quite large once the method bodies are written. It will be helpful if you can efficiently navigate large files like this one, and PyCharm garbage editor, so don't worry about that. Moving on. Now, task 1 is practice with linked lists. So in the starter code, find and read the docstring for method len, so the magic method which gives you a length of some object, and then implement it. You've already implemented this in the week's prep, but it's good practice to implement it again. And if you missed this week's prep, do it now. Okay. Then we have to implement count, index, and set item. And you might have noticed that all the doc tests were commented out in the previous part. This is because they use some more powerful initializer. Okay, so then we have to make some initializer. The lecture notes suggest to use it with, do it with append. However, we want you to do it without using append or any other helper method. Okay, so let's see. There are many ways you can do this. Key idea is that you loop through items, create a new node for each item, link the nodes together, and initialize self-dot first. Alright, spend time drawing some pictures before writing any code. Okay. And then task 2 is timing stuff. So timing the length for linked lists versus array-based lists, so regular Python lists. Most methods take longer to run on large inputs than on small inputs. Though this is not always the case. Look at your code for your linked list method. Do you expect it to take longer to run on a larger linked list than on a smaller one? And let's see, pick one of the following terms to relate to the growth. So basically the big O time, and justify it, and then complete the code in timeless. .py to measure how your running time for len method changes as the size of the linked list grows. Okay. Compare this to the behavior calling length on a built-in list. Start code begins this for you. What do you notice? Okay. Task 3 is augmenting our linked list implementation. So it makes sense our implementation is slow. How is the built-in faster? Turns out built-in Python lists use an additional attribute to store their length. So that whenever this is called, it simply returns the value of this attribute. All right. I just noticed this might be very small. Let's see, let me zoom into this. Okay, that's probably better. Okay, how's it faster? Okay, cool. Process of adding an extra attribute is called as augmentation. So changing the data structure basically, and it's very common in CS. Every augmentation poses a question of trade-offs. So the benefit of this extra attribute is it makes certain operations simpler and more efficient to implement. But the cost of the augmenting is that this extra attribute increases the complexity of the data structure implementation. So it makes it more complex, and it could add more steps in certain areas, right? And we'll get to that when we implement it. So create a copy of this class. You can pick a name and add a new private attribute length to the class, and then write down a representation invariant for this. Try to be precise without using the word length in your description. Okay. Update each mutating method. All right. Why do we have to not worry about the non-mutating? And enjoy the benefit of it. Okay, cool. Finally perform some more time tests. And then there's some additional exercises. All right. So now that we know what the lab is about, let's start it up. So task 1 is practice with linked lists. So I guess we'll start with this part. So if you open this up, and again, give this lab a try if you want on your own before you watch this, in case you want to implement it on your own. Otherwise, you can just watch this, I guess. So we have a typical node here, and then the linked list with the first attribute, which is the first node in it, and the initializer, methods from lectures and readings, is empty, the string method, get item, insert. Okay, cool. So this is all just from lecture. And then we have the length method. Okay, so let's implement this. So what we want to do here, why does my keyboard keep disconnecting? Okay, there we go. Back. Okay. So what we want to do here is find the length of the linked list. And what does that mean? That means find the number of nodes in our linked list, right? So we want to find let me get rid of that message. The number of nodes in our linked list. Okay. But the only thing we have access to is self.first, right? The only thing we have access to is self.first. So the first node in our list. So we're going to need like some sort of counting variable, and then we're going to need to iterate through this linked list and basically increment each time we find a new node, right? So let's, set some count variable. Okay. So let's do something like count equals 0. Or let's just do length, because that's what we're trying to find anyways. Okay, length equals 0. And then cur equals self.first. This should be pretty familiar. We're just setting up a loop to loop through the linked list, okay? And let's see. While so yeah, my keyboard kept disconnecting, so I plugged it in now with my cable. So back to this, we need to basically loop through our linked list, right? So we have our cur, which refers to the first one. So we do a typical loop, right? So loop through linked list, right? So while cur is not none, we basically need to do cur equals cur.next, right? This is just a typical iteration. Now, what we also need to do here is increment our length, right? Because we discovered a new node. So we'll just do length plus equals 1. And that seems about right. Now, and then finally, return the length that we computed. Okay, so we're just going to return length over here. And this is going to take linear time because we're looping through every single node in our linked list, right? So I'll just write big event just to keep track of it before. And let's get rid of that to-do because it's done. And let's go back to this. Okay. And now we need to implement methods count, index, and set item. Perfect. Just one thing. Let me turn on this. Okay. Perfect. All right, count. Return the number of times item occurs in this list. Use equal to compare items. All right, so we're gonna basically yeet this loop really quickly. And this loop is gonna be the main thing you'll notice in our code, because we're doing it by iteration. So we have occur again, some loop tracking variable, tracking variable, I guess. Loop through linked list, on, and return the number of times item occurs in this list. So now we need count variable, I guess, So far it's gonna be 0. That's what we initialize it to. And while cur is not none, cur equal current next, that's fine. But what we need to do here is check if it is equal to the item. So check if it is equal to the item. And here we can do that by, if we look at our node class, each node has an item, right? So we can just check if that item is equal to this given item. And so if cur.item is equal to item, we can just increment count, right? So if equal, increment count. And this is just moving on to the next item. And then finally, return the number of times that item occurs. So we just return count. And that's it for this one. And let's yeet the to-do because we're done it. Okay, next, index. Okay, return the index of the first occurrence of item in this list. Raise value error if the item is not present. Use equal to compare items. So I'm gonna yeet this because it's gonna be pretty similar. And we don't need a count variable this time. We do need this, And if cur.item equal item, we also need this. Actually, I lied. We do need some sort of count variable. But this is going to be the index variable. Because we want to count, what index it's going to be on, right? So if we look at these doc tests, if we have this linked list, then list.index at 1 is 0. Because we're looking for the index of that item, right? So we're looking at 1. Where does 1 occur? It's literally the first one, or that's the first occurrence, right? So it returns 0. Where does 3 occur? 0, 1, 2, 3. So it occurs on the third index. So it's we're returning 3 here. But we can't just do like a regular thing because this is a linked list, right? Everything's connected by links. So I guess this is actually a good time to draw a diagram. So let me do that really quickly. Let's do this. And okay, there we go. Perfect. Let me just make this a little bigger. Okay, cool. Now, so how are our linked lists drawn, right? So let's see. Linked lists. We have, some node here, right? And this is the first, let's say. And it stores some item, right? And if we look at this linked list, so 1, 2, 1, 3, 2, 1. Where is it? This would contain 1, and then this is like a pointer to the next one, right? So what was it? 1, 2, 1, 3, 2, 1, I believe, right? So 1, 2, 1, 3, 2, 1. It starts off with first, then it's going to point to a different one, right? Here, which contains 2. and then this is going to point there. Then there's a 1. So let's draw another one. 1. Point there. Then we have a 3. So 3. Then we have a, or no, wait, 1, 2, 1, 3. Yep, okay, I'm fine. Then we have a 2. Again, so 2. This points here. And then we have a 1 finally. And that points there. So that would be a linked list diagram of the given list, right? And then let's draw the indexes on a different color, just to be clear. So this is index 0. This is going to be index 1, 2, 3, 4, 5. Okay. So hopefully that's a good visual diagram for people who need a visual aid. Now let's go back to this. So let's move on. Yep. Okay. So where were we? Index. Right. So let's have some index variable. So index equals 0. And each iteration, we will want to increment our index. Okay. So index plus equals 1 here. And if cur.item is equal to item, then simply we just want to return the index because this is the first occurrence. So it's right here. If equal, return the current index because we found the first occurrence. Okay. And then if we get out of this loop, right? Like if we terminate this loop, what does that mean? That means we never, this if statement never happened, because if it happened, we would have returned, right? So that means that we did not find item in our linked list. So raise a value error. Okay. So here I'm just going to raise value error because we didn't find it. And okay, that seems good. So let's get that to do away. Now set item. Okay, so here we want to store the item at position index in this list. Raise index error if index is greater than or equal to the length of self. And what does that mean? If it's basically greater than the amount of nodes or things that are in this linked list, because then obviously we can't access it, right? Because it's not in our list. And let's look at this example. So we have a linked list of 1, 2, and 3. And this is equivalent to, and if we're calling list at 0, this is equivalent to list.setItem 0, 100. Okay, because 0 is the first is the index, 100 is the item. Okay, and then it's similar here. So string list is 100, 200, 300 because that's what we set it to. Okay, so here we're gonna do, this classic loop again. So I'm just gonna copy that, paste it here. We need an index variable. We need a current loop tracking variable, right? Loop through our linked list O of n again, while cur is not none. Now we want to insert it at, or we want to set the item at some index, right? So what I'm going to do here, well, these variable names actually conflict, so I'm just going to change this variable to idx for index, I guess. And let's check if we are at the index that we need to set at. So if let's see, if idx is equal to index, then if equal, what do we want to do? Set the item at this index. Set the item of this node. right? To item. So how do we do that? Well, cur is referring to this node, right? And cur.item is the item. And what we need to set it to is item, like this parameter item, right? And then we have this cur equals cur.next and index plus equals 1 to increment the index and move on to the next node, right? Okay, perfect. Now, if we reach the end here, you know, we would raise index error, right? Because we've reached the end of the list. However, this means that if our index is like greater than the length of the list, then it's still going to take linear time because we would have to loop through the list. And that's pretty bad. So what we can do is actually check that before we even enter this loop to make it constant time in case we have like a bad input, right? And one thing you'll notice is my camera or my face is on the right side now because I realized I was blocking the code somewhat. So I've teleported. Wow, magic, right? Wow. Okay, so here, before we do any of this, right, check if the index is valid. So if index is less than 0, that's invalid because we, for now at least, for now it's invalid because we don't have the capability of doing negative indexing. Or index is greater. Actually, this is a to-do. This is a to-do, okay? Because I just realized that we don't have a way of doing our length, getting the length, unless we call this length variable or length method, right? But that requires us to loop through our linked list anyways. So we'll get to this. Okay, we'll get to this, making it better. But for now, yeah. So if we reach the end, then raise the index error because index is greater than or equal to length of self. Also, here, once we reach the index and we set the item, then we can actually just return here. Because we want to stop the iteration, right? Because we've done what we need to do. We've set the item. So you can either do return none or return, then it's equivalent. Okay, so yeah, that's done. Cool. Now let's move on to the next part. So we've done this. You might have noticed that all doc tests were commented out in the previous part. They were? Oh, they were. True. I didn't notice that. Final task is to implement a new initializer with the following entries. Right, okay. Okay, here. With following interface. Okay, cool. So I'm just gonna yeet this actually. And put it here. And let's indent this properly. Okay, cool. Initialize new linked list with given items. All right. So let's do this. So let's iterate through the list. Okay. So iterate through the items list for item in items. Cool. Now, what do I want to do here? Okay. I want to basically create a new node. So node equals node and it contains item. Okay. Now what do I want to do? So here, let me add the comment here. Create a node containing this item. Now I want to add this node to be a part of our linked list. Okay. So what I can do, this is basically inserting right at the end. So since self.first starts with none, right? What I'm actually going to do here is have a loop tracking variable. Okay. And so we're just gonna call that cur like we've been doing it. And this is just going to refer to self.first actually to initially, okay? And which is none, to be honest. And then here we want to add it to be a part of our linked list. Now recall how we do that, okay? So what we're actually going to do here is let's see. Let's think. How can we do this? So we need some way of doing it for the initial one. Because, yeah, we would need some way of doing it for the initial one. So maybe I can actually do that here. Or I can actually handle that inside of here as well. Because list slicing is going to create a new list anyways. So I guess if cur is none, so this is the case where adding the first item in our list. So if cur is none, then cur, I guess we can do self dot first is equal to node. I think that works. And then cur is referring to self dot first, so it's going to refer to the same thing. And else, so otherwise, we are just adding someplace, right? So let's see. Then we can do cur dot next is equal to node. So whatever our current one is, we're adding the next one to be this new node that we created. Okay. And then we're gonna set cur to equal to this node, so that for the next iteration, it keeps following and it keeps making the link, the chain. And I think this should work. Yeah, I think this should work. So let me add a comment here. Otherwise, set the next node to be the node we just constructed. Or I guess otherwise add this item to the tail of our list. So set next node to be this new node, and then you know, increment the pointer, I guess. I don't think I need a comment for that. Okay, I think this should work. Yeah, this should be fine. Okay, I guess let's test it out. I guess I'll uncomment all these doc tests. I don't think there's a faster way to do that. Uncomment it, maybe. Oh, never mind, there is. I lied. So let's uncomment this. And let's uncomment this. And uncomment this. And this is one. So did I uncomment everything? Nope, I missed this one. And this one as well. Okay, I think that's good. Now import doc test as test mod. Perfect. Let's run this and see if it crashes. It crashed. Perfect. Alright, time to debug. 1, 2, 310, 200, -1, got 200. Alright. It's probably this one. So let's see if what happens if I do this. Actually, that's gonna mess it up as well. So let's do, and then maybe this. See if that works. Set item failed. Okay. Okay, set item failed. Did everything else pass? Okay, looks like everything else passed. So that fixed it. And what I did is basically the bug was that I was doing the self.first equals node, right? But this cur, it referred to none. And then when I did this, cur just became none, which is why I was getting an error. So I just redid cur equals self.first. And then we actually, yeah, we can do that, I think. Yeah, that should work. I guess I can do cur equals none here. And okay, and now there's a bug in set item. So let's see what that bug is. Index equals 0. Oh, index plus equals 1. Haha. Nice typo. Nice one. So IDX plus equals 1. Okay. Now let's run it. Voila! Now, you know what I should have done? I should have edited all that out, and then I would have had it on the first try. You know? But the real ones will know that I messed up. It is what it is. You know? It'd be like that sometimes. But at least I didn't make a post on Piazza asking why my code doesn't work. You know? 2:48 a.m. debugging sessions. We love those. Alright. Anyways. Moving on. Spend time drawing some pictures. Well, I drew one picture. I think that's good enough. There you go. That's a picture. Maybe I should screenshot this. Actually, I'll export it and put it after. Okay. Task 2: timing length for linked lists versus array-based lists. So most methods take longer to run on large inputs. Yep, although it's not always the case. Look at your code for this. Do you expect it to take longer to run on a larger linked list than a smaller one? And let's look at our code for it. Here, what are we doing? We're looping through the entire linked list, and it's taking linear time, right? So yes, I do expect it to take longer. Why? Because we're looping through each one. So as n gets larger, it's going to take a longer time, right? And I guess I can add a text file here. What is it? Task 2? Unless there's a thing in here. No, there isn't. Okay. Task 2.md. And copy this. Let me just format this really quickly. And then this is what, number 3. All right, perfect. Okay. Yes, I expect it to take longer on a larger linked list because I iterate through the entire linked list, and it is O of n time. So as n gets larger, it will take more time. Okay, and then pick one of the following terms to relate to the growth of lens running time versus the input size, and justify. So constant, logarithmic, linear, quadratic, or exponential. So I'll just pick linear because it's O of n, so linear time. Oh wait, I think I need to escape it. Cause yeah, there we go. It wasn't supposed to be italicized. Okay, there we go. And then complete the code in timeless by to measure how running time for your len method changes. All right. Maybe I should do that for all of them. Just to make it clean. Okay, there we go. Okay, I think that's okay. There we go. All right, let's complete the code here. Okay, let's see. What do I have to do? Return time taken to call len on a list of the given class and size. So list class and size, and if we look at how it's done, list class in list or linked list. From linked underscore list, import linked list. Okay, good. That should be solved if I just opened it differently. And create an instance of list class containing size zeros. Okay. So here, if list or if is instance list class list class is either list or linked list. Okay, I'm just doing this one line then, just to be cool. If it's a list, then I can do 0 times size. Else, I need to make a linked list. So let's do linked list, and it's actually going to be 0 times size as well. That's what we're passing in, and that's fine. Okay, call time it appropriately to check the runtime of len on the list. Look at lab 4 starter code if you don't remember how to use time it. Okay, so let's just get rid of this. That does that. Let's look at lab 4 code. Time Q. How do we use time it? Time it, number 1000. Okay, you know, plagiarism is beautiful. Let's do that. Boom. Now I need to do call len on it, right? Len my list. And I think that's fine. Okay, get rid of that to do. Try both Python lists and our linked lists for us in sizes. What sizes? Oh, okay. Okay, let's run it, I guess. It might error the first time I do it. Invalid syntax. Oh, I don't need the colon there. Okay, then let's run it again. Okay, it's running. All right, let's see. So list is taking, let's see, 0.13, 0.322, 0.69, 1.34, 2.29. Linked list 0.07. Why is our linked list faster? That doesn't make sense actually. Interesting. Did I only do linked list here? List S inside profile and list class S. Okay, I'm just gonna make sure it's doing it correctly. Okay, so it's making a link list each time for some reason. Is this not how I do? Is instance? Is instance? What's wrong with my syntax? Bro, isn't that what I'm doing? Debugging with Dave. Let's go. Linked list, linked list, linked list. What? It shouldn't be making linked lists. Why is this statement failing? Okay. If is instance object list class. If it's a list, we'd love print statements. Will it ever print here? What? What? Why won't it work? Bruh. For a list class. How is this not working? Am I not doing it properly? What the heck? Class type? Oh, is it because it's not an object? Ah, I see. Okay. So I don't need to use existence. I can just dumb it down even more. Nice. So if list class equal list, that should work. Okay, let's try that out. Okay, there you go. It's working now. It's working better. I'm just an idiot. Nice. Okay, so this makes more sense. If we look here, each of those length calls on a list, right? It's like instantaneous, right? But on linked list, it's taking like a shit longer of time. You know, it starts small because our size is small, but once it gets bigger, like 16,000, it's taking like almost 3 seconds, right? Okay, cool. So, okay, compare this to behavior. What do you notice? All right, let's fill that out. I notice that the list's inbuilt length is almost instant. However, my linked list length is garbage. All right, cool. Task 3, augmenting our linked list implementation. So now let's actually make it better. Our implementation is slow. How is it faster? Turns out it uses an attribute. Okay, so let's add an attribute. Create a copy of this class. You pick a name for your copy and add a new private attribute length to the class documentation and initializer. All right, so I'm just gonna, can I duplicate this? Let's do that. Let's call it goated list. Okay, and you know what I can do here? Replace all. Boom. Done. And then I need to add a private attribute length, right? So length, and it's gonna be an integer. Oh, what? And then let's add some private attributes here. So length, the number of nodes in this length list, because we don't want to use the word length to describe length. Okay, cool. So here, we need to modify this to set it to 0 here. And then for each item that we're adding, we need to increment the length. So let's increment that. So now this is like some more, you know, add default length. And then here we would increment the length. So increment the length, because we added a new node. Okay. Oh, write down a representation invariant. Yes. Okay, let's do that. Invariant. Is a non-negative number. I think that's fine. Can't be negative. Be precise without using the word length in your description. Is a non-negative number and represents the number of nodes in our linked list. I guess I don't know what else to say about that. I think that's good enough. Now let's put this on the next line just for formatting. Okay, update each mutating method to preserve your representation environments. Why do we not need to worry about non-mutating methods? So we don't have to worry about non-mutating ones because our length won't change for those, right? Our length only changes if we like delete something or insert something. Otherwise, it's the same, right? So that's why we don't have to worry about that. So I did the init is empty. This is non-mutating, so don't have to worry about string, also non-mutating. Get item, also non-mutating. Insert, this is mutating, right? So here I need to change something. So let's see. Here is where I'm doing mutation, right? Otherwise, here, let's see. We're inserting here as well. If cur is none, we're raising an index error. And if it doesn't raise an index error, that means it's inserting. So if I just add the incremental length at the end of this code, then that means that it can increment the length. So increment the length. So self.length plus equals 1. And that means I don't have to write it twice. Otherwise I would have to write it under here and I would have to write it here. But if I don't increment it, that means I raised an index error. So that's fine. Otherwise I'll reach the end of this code. Len, okay, we'll get to that. Count, count is just counting, so non-mutating. Index, also non-mutating. Set item, also non-mutating. Okay, so yeah, insert was the only one. Okay, now for length, what can we do instead? We can actually just return self.length because we're keeping track of it this time. So here, all my beautiful code. Bam, gone. Okay, done that. Done that. Finally perform some additional timing tests to demonstrate that you really have improved the efficiency. Sure. So time queue, nope. Timeless. Alright, let's just run this bad boy again. Oh, never mind. This is still running on the old linked list. But you know what we can do? We can import goated list, because that's actually the goated list, right? Let's import that one. Goated list. And here, I'll just add a goated list to our tests. Let's see how this works. Run it. So lists, again, instant, right? Linked list, dog shit, right? It's very slow. But look at goated lists. It's doing a little better, right? Not as bad as a linked list one. It's doing a little better. Okay, I thought it would actually be faster, but apparently not. Actually, yeah, I thought it would be way faster. Why is it taking so long? It's because it's inserting. Time at len of my list. Oh, no, I'm stupid. I'm stupid. That's why, right? Because, okay, look. Here, I was checking if the list class is a list, right? And then make a list. Otherwise, it made linked list. So obviously, it's going to take a long time. So I need to change this, actually. And I guess I have to use trivial this. Actually, what I can do, I can just set it to a list by default, right? And then otherwise, I don't need that if statement. So if it is a linked list, then my list equals a linked list of my list, which is just this. And if it is a goated list, then we can make it a goated list. That, and let me just add the if statements actually. So if list class equal linked list, and just press tab here, and then here equal goated list. Let me just oops, and then let me get rid of that print statement because I don't need it. Add some spacing between this so it looks better. Okay, all right, let's run this again. Now this time, goated list should be like instant as well. Yep, there we go. So list, instant, linked list, garbage, goated list, instant again. All right, so we're done with this. Okay, cool. Additional exercises: generalizing get item. Implementation we provide for get item has many shortcomings. Two features we want to implement are negative indexes and slices. So slicing and negative indexing. Modify linked list implementation get item so that it handles both negative indexes and slices. Note slice in Python is actually a class. The expression this is equal to that. Okay, use instance to use an integer or slice. Fully general, okay, sure. In the matplotlib practice. All right. Well, I can do this. This I don't know if it'll take too long, but hopefully not. I'll just do it in the linked list one. Actually, I'll just do it in my goated list one. I'll leave the linked list one as it is, because this is the goated list, so it should just be better than the other one, right? Let's Import that. Change that. Okay, that should be fine. Why am I getting error? Expect an indentation block. Why did it mess up all my Okay, there we go. I guess it's fine now. Okay, so let's see. How do we want to go about this? So we do need to check if it's a int or a slice. And if it's a slice, then we want to do a new one. Okay. If is instance index int, then we can do this loop code. Okay, I think that's fine. And then otherwise we can do slice. Otherwise do slice. Okay, and here our while loop will be somewhat similar. So let's see, while cur is not none, and cur index. Actually, wait, no, I lied. We can just use the same while loop. We don't need to do that. We can check if we need to do slicing down here. So in this else statement, basically. So if cur is none, raise index error, that's fine. Now here, if it's an integer, then we just want to return cur.item, right? Otherwise, want to make a new goated list, and basically, since we're making a slice, it's going to return a goated list. So we want to start at this index and keep going until the end of the slice. So we want to make a new goated list and return it. Now, index, since we need to assign the index here, okay? Because I guess I'll name this something else. So target index equals index if is instance index int. So basically, if the parameter index is an integer, then target index is just going to be the index, okay? Otherwise, so if it's a slice, then it's going to be slice at 0. Okay. So slice at 0. And I think this syntax start, stop. Let me look at the documentations for slice. So slice.start, slice. Let's see. Let's Google what the slice Python. What slice class, maybe? How do I access stuff of slices? That's what I want. Can I do this? Let's see. Let's play around with Python a little bit. Slice for x dot stop, okay, and x dot step, okay. So if I do x equals slice start stop, so let's do like index 1 4, then x dot start is going to be the first one, okay, and the x dot stop is going to be the last one. All right, that's what I needed. Cool. So here, I don't slices, recursive slices, that would make sense, right? Right? Or does it? Python's weird. Maybe it does. Let's see. 1 4. Okay, yeah, okay. That makes sense. Alright. You can't slice a slice. That would be weird. Okay, this is gonna need some more work actually to make it good. So let's do target index equals 0 if is instance this, target index equal index, else, or let's make this code even better. Target index can equal index if it's a slice, then we need to calculate what it is. So let's see, if slice dot start is equal to, if not slice dot start, so if not slice dot start, and this means we don't have a start index, then default it to 0. And then here target index is equal to 0. And then otherwise it's going to be just a start index. So I can make this better. So 0, or let's see, slice dot start if slice dot start else 0. Set it to the start index if it exists, otherwise 0. Okay, and let's do let's name this the start index, and then end index is equal to none for now. And if we do have a slice, then here the end index is just going to be slice dot end. That's what it was, right? Slice, or no, slice dot stop. Slice dot stop. And well, technically I don't need this. I can just slice dot stop directly, so I'll just do that. And this can just get renamed to target index again. Okay, target index equals index if it's a slice. So if it is a slice, need to change the target index Okay, cool. Now here, let's just change this to target index. And this is going to be target index as well. Now, of course, none, raise index error, because that means start is out of range. And here, if it's an int, then return cur.item. Otherwise, we want to make a new go to this and return it. Okay, cool. So here, let's see, what do we need to do? Do I have access to append in my linked list? No, right? No, because I would have to insert all the way at the end, and that takes a lot of time. Let's see. I know I need to start. Well, I could make a list here actually, and then convert it to a goated list. That's not the worst idea. But it's not just doing only linked lists, which is why I don't want to do that approach. So okay, let's just start with let's make a goated list. Oh wait, did I have the case? I do have the case. Let's make an empty goated list. Or well, let's put in the cur, right? Because we know we have at least one. This is going to be our starting index, right? Now our stop index is the one we're going to stop at. And how do I want to do the cur minus? And cur index is the one that we're currently at. So I can repeat this loop here. And we want to keep adding, so keep adding items until we reach the stop index. And so its target index is actually going to become slice.stop. So, or I could update my target index just until we reach the stop index. So I'm going to update the target index here to equal slice.stop. And it's the same loop. However, now I want to be inserting stuff. So cur equals cur.next. And then I can insert, but I don't want to insert none. So what I'm gonna do until we reach the stop index, and since we already added cur here, let's start with the initial empty list. Okay, then here, before I increment to the next cur, I know this cur is there's still something. Cur was none, there's an index error. So insert the current node, and so we can do gt.insert, and then this is the index and the item. Okay, so now I know the item is going to be cur. I lied, cur.item. We want to copy. Now the index, okay, so index is actually going to be 0 at the beginning, but how do we calculate this? So this is going to be cur index because we started off where we left off here, right? So it's going to be cur index minus the old target index, which was the slice.start. So maybe I should just keep this like a stop. Just to not confuse people. And then here it can be cur index minus target index. And then this is going to start off with 0, and then I'll go to 1, 2, 3, and then that way we can insert stuff into this always at the end of our list. And this isn't the most efficient way to do it, The most efficient way would just to be make a list here and then set it, make a go to list out of that. This is an inefficient way of doing it. So I guess I'll add a note here. But this only uses the linked list, right? Inefficient way of doing it, but only uses a linked list. And here at the end, I will just return GG. Yep. And inefficient way, okay. And now let's do a more efficient way. So efficient way of doing it, but uses a list as well. So here I'm going to add, let's see, new list equals empty, right? And this is going to be similar. Keep adding items until we reach the stop index. That's the same thing. However, instead of inserting on the linked list each time, I'm just going to be appending the item. So onto my new list. And the rest is the same. And then just here, before I return, I'm going to construct it with new list. So I'll keep both of these here, but I'll keep the efficient way. And this solves the slicing part, but it doesn't do the negative indexing part. Negative indexes and slices. Okay, we added slices. And I guess I'll add negative indexes. Negative indexes, we do it from reverse, right? So let's see. If it's -1, then we want the item at the end, which has the index length -1, right? So I can just change this target index here. So, and I guess I'll add the let's see, if is instance index int, then this can just go into else statement. Then if index is less than 0, then target index actually becomes self.length plus index, because index is less than 0. So it's basically, if it was -1, then it's doing self.length -1, which is the last item in our list. If it's doing -2, then it'll be the second last item, right? And otherwise it would just be the index. So I guess I can make this better again by doing that. And then if index less than 0, else it's just going to be index. Okay. Seems good. If it's a slice, so we need to change target index. Okay, I think this will work. But I guess I'll add some doc tests just to make sure it works. Let's try. 1, 2, 10, 200. Okay. List at 0. That's gonna be 1. list at -1, that's going to be 200. And let's just make sure -2, or let's do list of -3. That's going to be 2. And we need to take care of invalid indexes here. So let's just do if target index is less than 0 here, then raise index error as well. In case we're going too negative. If the negative index is too negative. And we basically don't have enough elements in the list to handle it. Good. -2, -3, -4, -5. I guess we can test that as well. List at -7. It's going to do index error. I'm just going to copy that into here. Perfect. And then let's do the slicing. Oh, okay, let's test if this works at least. Run doc test. Perfect. Run Python file. Oh, it works for that at least. Okay, now it's the slicing part. Let's see if I'm a god or not. Let's do 0 to 2. So this would go from 0, 1, 2, and it should just do 1 and 2. And I'm going to see the string version of sliced. And 1, 2, 3. So let's see. That should give me 1, 2. I think. Right, sliced is not defined. Why is that? Less than not supported between member descriptor and int. What? Is it not just an int member descriptor? What the heck? You probably don't want to use this function. Okay. How to get start, stop, step from a slice in Python. Is that not what I'm doing? Key dot what? get the start stop for I in X range this. Well, that's one way of doing it. Member descriptor and int. Okay, you guys can just like watch me debug for a bit. Can I cast it as an integer? Let's see. None type and int. Okay. Okay, this is gonna be fun. Alright. Maybe I should pause the video. Alright, let's pause and then magically come back to the solution. Okay guys, I'm just very stupid. Alright, found the bug. Okay, it's because I'm using slice.start here for some reason. Why? Because I thought it was a slice, but the thing is actually index. That's what it's called. It's not a slice. Ah. Alright, index. Alright, let's fix that. Index.start. I'm like, why was it giving me some weird ass thing? Okay, let's do that. And okay. Let's just start. Okay. And now here I'll do if target. Let's handle the negative case here as well. If it is negative, handle it. If the target index is less than 0, then target index is equal to self dot length plus target index. And okay, cool. And then here we're gonna check if it's too negative. You can check that over here. Move that over. Okay, good. And the rest of it should work as intended. Let's change that to index.stop. I guess we would have to do the same thing for that, right? Change that as well. And I'm gonna actually add a variable here called stop index because we need to add that change there as well, or the negative thing. So if stop index or index.stop, if index.stop greater than equal to 0, else self.length or plus index.stop, and then we need to. I'll do this. Yeah, I can do it over here. Or do it over here. Let's see, index.stop, if index.stop, else it's just gonna go to the end of the list. -1. No, it would just go to the end of the list, I think. Okay, and let's do that like that, and let's do stop index equal none. If it's negative, handle it. Okay, I'm just gonna copy paste that. And let's replace this with stop. Target, 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 target. And then this I need to change the stop index. And okay. It might be off by 1, but let's figure it out. Let's see. Expected 1, 2, got 1 comp. Let's go! It works! It's just, obviously there's supposed to be an error in between it. Alright, now let's look at if our negative stuff works. Let's see. Or let's see if I do this, it gives me the entire thing. It should give me the entire thing. I don't know if it will. Time to find out. 2, 10, 100? No, 200? Good. And let's see. Run it. 1, 2, 10, 200, got nothing. Okay. Okay. Now, why did it give me nothing? Let's self.length. That seems fine. This would never loop. That's fine. Okay, here while cur is not none and cur index is less than stop index. New list stop and cur.item, cur equals cur.next. Cur index plus equals 1. That seems fine actually. Wait. Why wouldn't it go? Oh, we did it? No, I didn't add the string of it, right? Yeah, I didn't do that. So many small mistakes today. Obviously that returns none. Stir sliced 2. Now this should work. Okay, that worked, okay. So now let's test the negative indexing. Slice 3 equals list -1 colon. So if I recall correctly, this should reverse it. Which won't work properly. Because we don't have reversing capabilities. But if I do something like -3 onwards, then that would give me what? 0, 1, 2, 3. So it should give me 2, 10, 200. Or -1 onwards, that would just give me the last one? Question mark? Let's see. Should give me 200. And then if I do slice 4 is equal to list 2, 3, 4, 4 till 3, 2, 1. 4 till 1, then it'll give me 1 to 10. So -4 to -1. Then it should give me 1 to 10. Let's see. 1 to 10? Alright, moment of truth. I'm actually a genius, guys. Look at this. Do I know what I just coded? A little bit. Am I sure it works? I think so. And let's try this inefficient way of doing it. Just to make sure that works as well. Hopefully it does. Nope, it does not work. Optional positional. Oh, here, let me do empty. This one didn't work. Why not? Oh, am I using the wrong variable names? I am. This should be stop index, right? Stop index, and then this should be actually, that's fine. Yeah, I think that was the issue. Okay, that one works as well. So okay, so both the inefficient one and the efficient one work. I'm just gonna keep the inefficient one commented out, and I'll uncomment this one out. This could be better. Okay. O of n max, right? And this while loop is also O of n, so it'll be n squared in total. Whereas this one is O of n, but then this is constant time, which is why it's more efficient. And well, technically this takes O of n as well, but that's fine because that's linear, so it's still linear. And I'll just add this here. Okay, I think that's it with the lab plus the extra example. This was a really good example actually, or exercise. Took a while. MATLAB prepare. Okay, I'm not doing that. That you can do on your own. Actually, should I do it? Maybe I should do it. Just for completion purposes, I'll do it. But I'm not writing the code again, so I'm copy pasting it. Let's see, how do I want to do this? Alright, what do I need to import? I need to import .pyplot. Make a figure, and then let's see. Here I want to do times.append time. That's fine, and then here I can do plt dot I need to make a dictionary, so all times dot append. Okay, and then I can do all times at this equals times. Then I can plot stuff down here. Let's do this. Or I can plot stuff in here, I think, as well. Then I don't need that. And let's try that. PLT.figure. And here, time, because that's fine, that's fine. Okay, now here, plot stuff. PLT.plot sizes. And then times. PLT.x label. Sizes of the lists. And PLT.y label is time. And then PLT.subtitle. That's just gonna be, let's do f string. List class dot name. And yeah, okay, let's try running this. What I need is the app of it. Or okay. Oh, I didn't show it. That makes sense. PLT.show. Let's run that again. Okay, so this is the one for the list. You can see 1e to the -5, so this is like very small. So there's not really a difference. Then once we run the linkless one, you can see it's linear time here. This is in seconds, right? Starts off small, then goes up to like 2-ish seconds. And then this is the goated list. It's like instant again. Yeah, and then actually let me save those figures just for your sake. List time. Where is it? Document this, nope, wrong one. This one, this one, this one, this one, and save. Okay, good. Let's let the linkless one run. Okay, linkless. I'm gonna save that as well. Linkless, save. Okay, good. And close, and let's save the goated list one as well. Goated list. Right. Save. Okay, good. And that's it. And what else? What else? What else? Should I copy the results? Nope. Actually, that's fine. Okay. I think that's it for the lab. Let me just rename that file. Okay. Cool. That's it for the lab. All of this code will be pushed to the repo. And yeah, we covered everything in the lab. All right. Well, hope you enjoyed watching this and have a good night or whenever you watch this. Thanks.